All right, in this chapter, chapter 2, we're going to talk about the electrons and the periodic table. Last chapter, we took more about the atom itself as far as protons and how it's arranged, but we're going to spend most of our time now on the electrons because that's where the chemistry occurs. All right, so we're going to talk a little bit about the history of electrons and this branch of physics slash chemistry called quantum mechanics. It kind of came out about 120, 130 years ago, which kind of explains the electrons, and it's a weird type of way to think about physics. So we'll kind of talk about the history, and we'll talk about how light kind of the research that was done on light kind of helped us kind of figure out the how the electrons behave and about the atom. And we'll talk about Niels Bohr, who kind of came up more with the way that we think about the atom now. We'll talk about orbitals, electron configurations, and something called orbital diagrams. They don't particularly use that word, but I will be using that word. And how it relates to the periodic table and how the periodic table is organized and some trends. And then we will talk about what ions are. All right. First of all, let's talk a little bit about light. All right. Light is forms of waves. Waves of energy is how we see light, or that's how they did see light prior to about 130, 150 years ago. And you have two things that describe light. One is the wavelength. All right. That's kind of how long the waves are. So do you have really long rolling waves? All right. So the wavelength is from one point to another point. So that would be one wavelength. Okay. Or do you have really smaller wavelengths? All right. So you have a much smaller wavelength. All right. And that is shown by lambda, the Greek symbol for lambda. So that would be a big wavelength, and this would be a little tiny wavelength. We'll kind of make it smaller. Okay. Then you have a frequency. A frequency is the number of wavelengths per unit of time. In this case, we'll talk about a second. All right. So let's just say this is a unit of time right here, and this is 1 second. So here's from 0, here's to 1. All right. And it looks like we really have only like about one wavelength in that second. Let's say here's the other one. You can see we have 1, 2, 3, 4, 5, 6 waves per second. All right. So this has a very small frequency. Nu is the Greek symbol for this one. Nu. It looks like a V, but it kind of should have this little tail, I guess. And this has a very large nu. So you see these are opposite of each other. If you have a big lambda, you're going to have a small nu. They are inversely proportional to each other. Okay? And if you have a small lambda, you have a big nu. Right? See that? Inversely proportional. All right. So now we have another unit, which is energy. So we first have the wavelength, how big it is. Then we have the frequency, how many there are. Now we have energy. All right. And energy is directly proportional to your frequency. Okay. So small frequency, small energy. Big frequency, large energy. Okay. These are directly proportional. So if you have a lot of small waves, boom, 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 just going. Big energy, all right, high frequency, small lambdas, small little waves, but boy, there are a lot of them. Okay, so that would imply a lot of energy. That kind of makes sense. This, you got these big, slow, well, they're not slow, they are both at the same speed, at the speed of light. You get these big, huge waves, but you don't have as many of them, so therefore you have small energy. Okay, so that's how all three of these are related to each other. Okay, so here again, it just kind of shows you examples of that. Here is a lambda, from here to here is lambda A, and then from here to here is lambda B. So it's kind of showing you that the wavelength increases, the energy decreases. So remember, it's an inverse proportional. So small wavelength, all right, which is what we have here. All right, so as our wavelength increases, so large wavelength, this is a large, so it's increasing. Small wavelength, small energy, and then as it decreases, or as our frequency increases, notice in this example, they're very frequent. Waves are frequently happening, so large energy, large frequency, large energy. Okay, so that just kind of is a summary of what I just talked about. Okay, so here's the line spectrum. Everyone kind of knows the line spectrum. Anytime that you've drawn a rainbow, all right, a rainbow's always in these colors. You've got red, you've got orange, you got yellow, green, blue. This is called indigo, which is kind of a bluish, purple color, and then um, violet. We call it violet, I guess. All right, you've heard of this Roy G. Biv. I'm doing it backwards because it's just showing you. All right, so red, orange, you can kind of see the orange color, yellow, green, blue, indigo, violet. All right, Roy G. Biv. And the red side of this is the lower energy. Okay, so these are big lambdas, all right, small frequencies, small energy. Where on this side is the opposite. You got smaller lambdas, all right, you've got big frequency, small energy. All right, you see how showing you the wavelength? Small wavelengths, smaller wavelengths than your 700. Okay, so violet is higher in energy. Now, you guys have heard of ultraviolet, right? UV is the energy wavelengths just above violet. That's why it's ultraviolet. Ultra meaning above the violet. And then, do you know what's underneath the red or lower than red? It's called infrared. I know you've heard of infrared, and I think we show this in the next slide, but just to kind of tell you now, infrared is much lower energy. This is more like heat energy. Okay. A lot of animals are able to see in the infrared region. Okay, mostly birds are able to see that. I believe snakes are able to see this. Birds kind of see it because it shows heat. All right, anytime that you've put on or have ever seen anyone put on like night vision goggles, you know how they kind of everything's black, but then it shows you this white glowing object. That's the heat wavelengths. That's the infrared wavelengths that's coming off of the animal. So birds are able to see this because they sit really high in trees and they look down at the bushes and they see black with the exception of a little bit of specks of white, which are the animals. Some animals can actually see in ultraviolet regions as well. Okay, so I want to say snakes can actually see in ultraviolet. I don't remember, but a lot of we can't. We can see in the visible region. This is the visible region. All right, so we see color. So right now, you see this as red, as long as you aren't colorblind. You see this color is red, even my pen is red. Well, what's going on is all the wavelengths of light, all these wavelengths of light are hitting your computer, and only the red wavelength is bouncing off of this. So only the red wavelength is all bouncing off of it into your eyeball. That's kind of, I'm trying to draw a picture of your eye. Here's your eyelashes. Okay, so we're just seeing the red wavelengths bounce off of this. So over here, I'm seeing the violet wavelengths bounce off. I'm seeing the yellow wavelengths. So that's what our eyeball is seeing. All the other wavelengths are being absorbed into the page, but only the certain wavelengths are coming out. Okay, so here's kind of more of an extended view of light. I'm sorry, of the electromagnetic spectrum, which light is a very, very tiny part of it. You see how small light is? So you've got radio waves, which is the biggest portion of it, and radios work off this. Anytime you do an MRI, MRIs actually work off of radio frequencies. If you ever had an MRI, it says if you have magnets or if you have a pacemaker, make sure you don't go in there because the radio waves, they're very high intensity. It's a lot of them in one spot. Cell phones are kind of radio waves / microwaves. All right, we are filling up all of our bandwidth with the amount of people and the amount of cell phones and the amount of radio waves and a lot of other wireless devices that we use are taking up kind of the radio wave real estate. So we're starting to use microwave energies or wavelengths to use our phones as well as like our satellite, like the dishes that we put in our house. All right, infrared is really heat energy. You can see heat lamps provide heat lamps. If you ever go to a fast food joint and all the food is underneath those red lamps, well, those red lamps are producing infrared as well as a little bit of red light. Ultraviolet, I guess, they're talking about sun lamps, like if you go and get a tan, but pretty much our sun you know that, so a little portion of the ultraviolet region is kind of all starting to get through our atmosphere. All of this is energy so all this our sun produces, but only this amount of it is what is allowed to pass through our atmosphere. All the other wavelengths, most of the ultraviolet, X-rays, and gamma rays are blocked by our atmosphere. All right, our atmosphere is able to block them. X-rays you can only do when you produce it from a machine. When you take an X-ray of a bone, here's an example, or your teeth, very, very, very small amounts of X-ray, because X-rays, the energy actually is able to travel through our skin and our tissue, but our bones, it hits the bone and then it reflects off. So that's why we're able to see a picture of our bones when we take X-rays, but you don't see your veins and anything that is like our tissue. All right, and that's because the X-rays kind of go right through it, and it really has no effect. I mean, it kind of like destroys it a little bit, but not much, because we're talking such a tiny amount. Gamma rays basically go and they destroy everything. All right, it kind of goes through you. Gamma rays, really the only people that experience gamma rays is if you are a cancer patient and you have a tumor and they're trying to zap the tumor. They actually line it up perfectly and they zap the tumor with your gamma rays, and just enough of it just to kill the cells inside of the tumor. Okay, so that's kind of where gamma rays are used. Other than that, we are not exposed to them. If we were, we would pretty much die very quickly. Okay, so that's kind of the line spectrum. This is kind of talks more about it. It basically says anything that is visible to us is either radiating or reflecting visible light. So like I talked about, the red region, okay, so if I put a red color here, so all of the wavelengths of light are hitting this, but only the red wavelength is bouncing off of it, and we're seeing it in our eyeball. Okay, that's the reflection part of it. The radiating part of it is if you have a firework and you light a firework and it goes up in the sky and explodes, and you see red colors, or you see green colors, or you see blue colors. All right, what's actually happening is the chemicals inside are absorbing the heat of the fire that's making it explode. All right, and it's exciting the electrons into higher energy levels. We're going to talk all about this and kind of show it to you. And then when those electrons relax into their relaxed state, because electrons don't like to be in high energy states, when they relax, they release, they radiate the energy that they absorbed. So if they absorbed the red wavelengths, and once the electrons relax, it's going to release those red wavelengths. And that's what our eyeball sees. It sees this radiation of energy, of light, all depending on the chemicals. Okay, so it says that in a similar fashion, we use to separate white light from the sun into its components, into the Roy G. Biv. All right, it also tells you that certain chemicals, so neon, actually when you excite it, it releases a red light. So all different chemicals absorb and release different energies of light, and they radiate off or reflect off the different colors, all depending on the emission spectrum. Okay, so we are going to talk about that. All right, so let's see down here, emission spectrum that are not continuous but contain only discrete lines, such as neon. It's called a line spectra. I believe we're going to talk about a line spectra right now. This was kind of huge. They didn't know about this. This was kind of huge into kind of coming up with the quantum era. All right, what it's basically saying is, all depending on the chemical, it absorbs certain energy levels or certain wavelengths of light, which is characteristic for that chemical. All right, so here's kind of a line spectrum. They don't really tell you what they are, but we'll just pretend. All right, so here's a line spectrum down here of just all of the wavelengths of white light. Oh, white light. Okay, if you were... Everyone has kind of seen this, especially if you are a Pink Floyd fan. You've kind of seen white light going into a prism, and then coming out of it at an angle are all the different colors. All right, like the Dark Side of the Moon album. Anyone into Pink Floyd or have seen that? Okay, that's basically what's going on here. All the white light is all coming out in all the forms of the wavelengths. These are different elements. All right, I'm just going to assume that this is hydrogen here. I don't know if it is, but let's just say. Okay, I don't have a key somewhere. Notice you only see 4 bands. You see a purple, you see a blue, you see kind of a lighter blue band, and you see a red band. And those are the only 4 lines that you see. All the other ones are blacked out. Up here, you kind of see a few more bands. You can kind of see a few down here. You see 4 here, you see a few there, you see 1 there. You kind of see like a yellowish green and a red. All right, here you see a lot more, especially in this region right here. Okay, certain elements absorb these different energies of light. All the other light just kind of passes through it, but this hydrogen, for example, is just absorbing these wavelengths. So that's the color that we see. Okay, if you've ever wondered when like an not astronaut, but when they say that they have like discovered a new planet, and they say that the planet is filled with hydrogen. Do you ever wonder how they know it's filled with hydrogen? I mean, how do they know? They obviously haven't gone to it. Well, this is how they do it. They look at a telescope and they put a line spectrum on it, or kind of like this, a spectrum, and whatever wavelengths they see, they can tell, because hydrogen has just this characteristic. It's kind of like a zip code. If it looks like this, it's hydrogen. It's no other element. There's no other element that has the exact same wavelength as hydrogen. It's just hydrogen. All right. If they do it and they see this, let's say this is helium. I have no idea if this is helium, but let's just say this is the spectrum for helium, and this is what they see when they do the spectrum on the planet. Then guess what? There's helium on the planet. Okay, so that's how they can identify what elements are on planets, is based off of this line spectrum. And this was kind of big because this kind of told them that these elements, these electrons in the elements, are interacting with light in a very specific way, very specific energy wavelengths. It's not just random. Okay, I'm going to pause it right here, and this will be the end of the first video, and then we'll talk about the Bohr atom, which he took this information that they learned from light and kind of extended it into electrons. And we will see that on the next video.